In this example, we are going to derive the full equation of motion for this 1 degree of freedom system. We see here that the makeup of our system is more complicated than in the first example. We have this bar that can rotate, we have the mass m1, a mass m2 that can move, we have springs involved here, there's going to be rotations, there's going to be translations, all of that in this system. So where we want to start analyzing how is this system going to move is by drawing a schematic of that motion. So it's presented to us in this equilibrium state. So I'm going to just draw the bar for right now so we can study how does our system behave, how does it move. Right, so in its equilibrium position here, x, which is ultimately what the degree of freedom we want everything expressed in, x is the translation of cart m2, the horizontal translation. So x is positive, m2 moves to the right, x is negative, m2 moves to the left. So what happens if that cart moves to the right, let's say? Well, that's going to cause this bar, this J0 bar, to rotate. The bottom will kick out to the right, which means the top must go to the left. So in my perturbed system, that's going to be the rotation of that bar. In this example, we are again going to be assuming or treating things as a small angle of rotation, which means that when it rotates by an amount I'll call theta, and theta I'm going to define here as positive counterclockwise, that bottom of the bar moves strictly to the right, and the top of the bar moves strictly to the left. Now the bottom of the bar is already defined how much it moves, because if we see the cart M2 is rigidly attached to the bottom of this bar, so if M2 moves to the right by an amount x, that means the bottom of the bar must also move by an amount x, because the thing that connects M2 to the bar, we're going to assume cannot deform. All right, so that is going to be defined as x, and this is going to be a right angle, and this will be a right angle. And again, because of small angles of displacement, that means that the top of the bar is going to move an amount, or is going to move purely to the left. However, because A and B are not necessarily equal, they don't have to be, as is defined here, the top of the bar can move a different amount, and I'm going to call that amount x2 in this. So I'm inventing a new degree of freedom, x2. I also invented a new degree of freedom, theta. However, we're going to see in this one that they're all going to be related to each other. There really is only one independent degree of freedom here. We are told to make x the one we analyze everything in, but we could do everything in terms of theta. We could do things in terms of x2. Right, so again, the important thing here is, once again, I'm going to assume or treat this as a small angle of rotation, theta. If it was a large angle of rotation, then I cannot say that the bottom moves purely to the right and that the top moves purely to the left. There would be some arc to it that would be non-negligible. This is actually enough to get started on writing out my different energies, which I'm going to need to get my equation of motion, because we're going to use Lagrange's equations. So I'll start with my V equation, although the order really does not matter. So potential energies in our system. First, let's look at our schematic and see what is going to contain potential energies, so we know how many terms we're going to need here. We have three things that are springs directly. K1 and K2 are linear springs. KT is a rotational spring, or we could call it a torsional spring. M1 and M2 only can move horizontally in this example, so their center of mass cannot change height, so they definitely do not have any potential energy in them. And then the bar, that J0 bar, we're going to treat as having negligible mass, so the height of it is not going to change. And also, because we are assuming small angles of deflection, the center of mass of the bar would not have any change in its vertical position, only its horizontal. So V is going to have a total of 3 terms, 1 for each spring. So let's look at M2 to start, or K2 to start, which is attached to M2. So we want to account for the spring potential energy in K2. Right? It's going to be 1/2 times the spring constant times how much K2 has deformed. Well, it's attached to the wall on the left and M2 on the right. So the wall doesn't move, so it's entirely dependent on how much the right end of that spring moves. M2 is attached to degree of freedom x. So the total deformation of K2 is going to be x squared so that we can find the energy of it. So 1/2 K2 x squared is the potential energy, the spring potential energy in K2. And that's it. Now we can add the spring potential energy in, let's look at K1. So it has a coefficient of K1, the 1/2 is out in front. How much does K1 deform at any time? Here, the left-hand side is attached to a wall, that can't move. The right-hand side is attached to M1, so the right-hand side is the only thing that can move. M1, if we look at the schematic we drew, M1 is attached rigidly to the top of this bar, this rotating bar, and we defined the motion of the top of the bar as x2, and I defined it as positive left in this example. Again, it's an energy equation, so it gets squared, the deformation does, so it doesn't matter too much if x2 is positive or if it's negative, but the right-hand side is going to deform by an amount x2. Whether x2 is positive, meaning that the spring is being compressed, or x2 is negative, meaning that the spring is being extended, again, doesn't matter because I'm squaring it when I'm finding the energy. So the energy, the spring potential energy in K1 is 1/2 K1 x2 squared. And then I have the third spring. It's a torsional spring, so it will depend on the angular displacement. So it's going to be 1/2 kt times the angular displacement squared, and the angular displacement must be measured in radians, assuming kt is going to be in radians, in moment per radians. Right? And it's going to rotate through an angle of, as I defined it in the schematic, theta, and that will get squared. So I invented these 2 extra degrees of freedom from what I was given, x2 and theta. Both of them are featured here in V, and I'm going to need to convert, though, everything to x before I actually do the differentiation, which I'll do, I'll wait to do that part. All right, now I want to assemble my kinetic energy. I'll put V aside for now, and I'll convert it in a bit. Now, in T, the kinetic energy, I need to account for everything with either linear kinetic energy or translational kinetic energy, and then the things that have rotational kinetic energy. So if I look here, starting at the top, M1, that cart has mass, and it can move only left or right. It cannot rotate the way that it is set up there. So M1 will contain translational kinetic energy. M2 is going to have the same idea. It can move left and right, and that's it. It cannot rotate, so M2 will have translational kinetic energy. And then we have that rotating bar, that J0 bar. We are told to treat it as having negligible mass, so we are not going to consider its translational kinetic energy because the mass is basically 0. However, we are not told to neglect its inertia. It is going to be rotating around its pivot point. So it will have rotational inertia that we need to account for. So we're going to have 3 terms here, 2 of them translational kinetic energies, and 1 of them rotational kinetic energy. So let's look at, in the same order as we did before, let's look at M2. What is the kinetic energy in that cart? Well, the general form for translational kinetic energy is 1/2 mv squared. So 1/2, its mass is m2, and now the velocity of m2 is defined by its degree of freedom. So m2 has a position of x. So its velocity is the time derivative of x, which gives us x dot. So its x dot squared is always talking about its velocity. Once again, if it has velocity to the right or the left, the kinetic energy doesn't care. Then that term is being squared, so the sign on it is not going to matter. So that is the translational kinetic energy of M2. Right, now let's look at M1, also going to be translational, 1/2 times its mass of M1 times its velocity. Again, its position of the position of M1 is defined only as x2. So the velocity is x2 dot. And m1 only has translational kinetic energy, so that is the second term. All right, and now we are counting for the rotational kinetic energy of the bar. So that's in the form of 1/2 I omega squared for rotational kinetic energy. So 1/2 times the mass moment of inertia, which we are given to be J naught. We're not going to calculate it. We don't know if it's a cylinder or what it is. We're just told it's some value J naught. And now we need the angular velocity of the bar. Well, again, its rotational position is going to be theta, so its rotational velocity, or its angular velocity, is theta dot. And then again, that will get squared. Okay, so at this point we have our v, we have our t, but we have a mixture of the degrees of freedom that they're expressed in. There's an x, there's an x2, there's a theta. But we need everything in x before we can find the equation of motion, because we can only do our partial differentiation with respect to one independent degree of freedom. So we're going to need to establish some geometric relationships between the two degrees of freedom we need to eliminate in these equations and the one we want, x. So let's start with x2. How can we eliminate x2? Well, if we look at our schematic, we can see that we actually made two similar triangles. They both have a right angle and they both have theta, the top one and the bottom one. So we can use the similarity relationship between triangles, that the ratio of legs are going to be equal in similar triangles. So if I look at the bottom triangle, I have a leg that is going to be x, and I can divide by that vertical leg b. And that ratio must be the same as the corresponding parts on the top triangle, which would be a leg of x2 over a leg of a. So rearranging this, I'll be able to eliminate the x2. I can multiply by a. So x2 is a over b times x. Now, so that'll be one substitution I'll be able to make for v and for t. And it's also going to be true while I'm here. I can take the time derivative of the left side and the right side. A and b for here are constant. They don't change in time. So they are going to be able to come outside of my time derivative. Now, in a more complicated problem, it is possible that a is a function of time and or b is a function of time, and I would have to use product rule or quotient rule or both. But in this case, they're both constant with time. So when I differentiate both sides, it just stays out in front. And I need that for my t equation. Now, I need a relationship between theta and x. And for this, I'm going to be able to use trig to establish that relationship. So for example, if I have x over b, from the viewpoint of theta, that is going to be opposite over adjacent. And we know the trig property, opposite over adjacent, that is the tangent. So if I take the tangent of theta, the tangent of theta is the opposite leg over the adjacent leg. Right, so if theta is large, this is the expression I'm going to have to use, although in this case, if theta is large, x is not really going to be an arc, x is not going to be a straight line. So I'm already using the assumption or the limitation of a small angle approximation. So what this tells me is that for small angles of theta, as an aside here, the limit as, let's say, theta approaches 0 of the tangent of theta, remember this from the first calculus course, is going to be theta. So for small angles, tangent of theta approaches theta when theta is measured in degrees. Also, it's important to remember the other relationships here. The cosine is going to, in the limit, be 1, and the sine in the limit is going to be theta. Right, so small angle approximations, we can make the trig terms basically go away, and that's, again, nice here because we're going to see that now we're not going to have a trig term when we when we put it into our v and into our t. Right, so x over b equals theta for small angles. And again, I can differentiate both sides. So x dot over b is going to be equal to theta dot. Right, so small angle approximation lets us approximate tangent of theta as theta. Now, the error increases the larger that theta gets, but generally, if our theta value is, as a rule of thumb, 5 degrees or less, plus or minus 5 degrees, then we're within a fairly small amount of error that we are introducing into our system. Right, so with our geometric relationships here, I will be able to substitute x2 out and x2 dot out, and theta out as well. So now I can, let's go to v, and I can rewrite v. So 1/2 k2, so the first term is already okay, x is what I want everything in, plus 1/2 k1, now x2 is a over b times x. Right, so I want to be careful here. I have an x2 quantity squared. I need to square that whole quantity of a over b times x. So I'm left with an a squared over b squared times an x squared, plus a 1/2 kt theta squared. Theta, that quantity, is x over b. So I'm going to get here a 1 over b squared times x squared. And we'll see in a second, remember why I wrote it that way. I want to write this in a convenient form for the next step. So I'm going to actually pull a 1/2 out in front, and I'm going to pull an x squared out in the back. So I am left with a k2 plus k1, a squared over b squared. The x squared I'm going to pull out to the end, and then my third term, the 1/2, is out in front. I have a kt over 1 over b squared. I'll just combine those. So I'll have a kt over b squared, and then that x squared is on the outside. Again, we'll see why this is useful in a second. So again, my v now I've rewritten only in terms of 1 degree of freedom, that desired degree of freedom, x. And once again, I'll put v to the side just for the moment, because I now want to rewrite my t only in terms of x. The first term is okay. It already is only in, I want in x dot. So already it has my x dot. Now my second term, 1/2 m1. The x2 dot I want to substitute out. I know from before x2 dot is a over b x dot. So again, I need to square that whole quantity. So I have an a squared over b squared x dot quantity squared. And then my last term, I have a 1/2 j naught theta dot squared. That is going to be 1 over b squared x dot squared. So like with the v, I'm going to pull the 1/2 out in front. That will help when I do my partial differentiation, and the x dot squared to the end. All three terms are now in terms of x dot. So I have an m2 plus the 1/2 got taken out, m1 a2 over a squared over b squared, plus the 1/2 is out in front, j naught over b squared. So now my t it's in the form that's going to be useful for the next step. I have an x dot squared at the end. That's now my only time-dependent variable is x dot, and I have a 1/2 out in front. Now, v has been rewritten in terms of just my desired degree of freedom, and t has been rewritten in terms of just my desired degree of freedom, x for v, and then its time derivative x dot for t. Now I can go on and apply Lagrange's equation, and we're going to see I'll be able to find the equation of motion for this system. Right, so the form that we're going to have it in is going to be, I need the total time derivative of the partial derivative of t with respect to my independent degree of freedom x dot, plus del v del x. And this is an autonomous system, so the right-hand side is 0 here. All right, so this is my Lagrange's equation, and I didn't want to get to this step until now because I needed v and t written only in terms of the same independent degree of freedom, which I chose to be x. Once again, I could have done, at this step, I could do everything in terms of x2, I could do everything in terms of theta. We just chose to do it in terms of x. But I know the conversions between x2 and x and theta and x, so later, if I really did want to track the angle of my bar, I could convert everything into theta later. But I wanted in terms of x for this example. All right, so let's do this step. Now, the way we wrote our t and our v is really convenient. So if we look at, let's start on the inside here, I have a del t, del x dot. So remember, when we're doing partial derivatives, anything that we're not differentiating with respect to is considered a constant. So I need to take my t and I need to differentiate it with respect to x dot. Well, I have here an x dot squared. So when I differentiate it, that 2 will come down and cancel out the 1/2, and I will be left with just an x dot. So it's going to be this constant, m2 plus m1 a squared over b squared, plus j naught over b squared, x dot. All right, so that is after I do the partial derivative. Now, now that I have this, I have to take the time derivative of this whole thing. All right, well, m2, m1, a, b, j naught are not functions of time. We're assuming that over time the masses are constant and those lengths are constant and the inertia is constant. So the only thing affected by that time derivative is my x dot, and that will then become x double dot. That's the time derivative of velocity is going to be acceleration. Plus, now I want my del v, del x. So again, looking at how I wrote the v, I have my x squared at the end. The partial derivative of x squared will be 2x. So the 2 and the 1/2 are going to cancel each other. So I'm left with this coefficient here, k2 plus k1, a squared over b squared, plus kt over b. And again, x squared goes to 2x, but it cancels out that 1/2, so x. This term will be my m equivalent. I'll just write m for now. And this stuff in front of x is going to be my k equivalent. So this simplifies down to this generic looking mx double dot plus kx equals 0. Any 1 degree of freedom system is going to look like this. So really our job in the modeling step, in this step here, is to figure out what is that equivalent mass, what is that equivalent k. So that's why we went through the Lagrange equations, why we came up with the t, came up with the v, so that we know what those are actually made of there. So the m equivalent is made up of the individual masses and the inertias, but put together depending on what the geometry of this scenario is. And our equivalent k is made up of the individual spring constants, but again, it depends on the makeup of the system, how they are all connected to each other. It's not simply k1 plus k2 plus kt. We have to go through all the geometry to figure out what the ratios, what the combination is. So in the end, we have our differential equation, or our equation of motion, but really what we were caring about was finding equivalent mass and the equivalent spring constant with respect to x being our independent variable. At this point, if I still wanted to, I can now go and convert my x and my x double dot into theta or into x2, and I could have a different equation of motion with respect to the theta or with respect to x2 if I wanted to do it that way. But this is really what we're trying to get at in the modeling step, is getting our ordinary differential equation, knowing what these equivalent values are. In the next sections, once we get to this point, then we're going to be interested in actually solving it for x of t. But for now, the end of the modeling step is the ODE, or the equation of motion, for the system.